Hello, this is Mr. Huff, and we need to talk about water supply systems. So the first thing we need to know is static head. So think about head as being the amount of pressure as a result of height. So it's measured in feet of water, and that can be converted to psi. It's similar to the ideas of potential energy. Yeah, mostly potential energy. It's similar to that idea, stored energy. Okay. So to calculate the static head, you need to know the change in elevation in feet. And an example of this would be on this graph. I've got a little drawing here. So let's say that this is a water tower, and then the water system goes through the ground to the house, and the difference in altitude or the difference in elevation between the water tower and the house is, let's say, 100 feet. So right here, this red line would represent 100 feet. To convert between feet of water to pounds per square inch, 1 psi is equal to 2.31 feet of water. So if you have 100 feet of water times 1 over zero point 0.2 or 2.31, so 100 divided by this, you get 43.29 psi. So 100 feet of water is equivalent to 43 pounds per square inch and some change. All right. So that's a conversion you will have to do. You need to be able to convert back and forth between PSI and feet of water. To calculate the actual pressure at the house, you have to accommodate for the static head, which is the amount or the feet of water based on this height difference. And you also have to find something called HF, and this is the loss of head due to friction. So as the water moves through these pipes, it encounters friction. There's two places it gets friction. One is from the walls of the pipe, especially if they get rough. There's more friction there, so it slows the water down. And also, as they move through different fittings, as they go through elbows and in 45-degree turns and valves and that sort of thing, they lose that includes friction and will reduce the static head value to the actual head. So to find actual head, you need to find static head minus the friction loss because of the system. So this is where it gets interesting. So let's take a look at the formula right here. So the friction loss is going to be equal to the number 10.4 times the length of pipe times the flow rate of water raised to the 1.85 power divided by the product of the Hazen-Williams constant raised to the 1.85 power times the diameter of the pipe raised to the 4.8655 power. Okay, so let's turn this off. Let's look at what all these numbers mean, just reviewing that. So this is the formula we're looking at right here. And let's go look at the meaning of these. So when we talk about length, we're talking about the equivalent length of pipe in your system. This formula only works for straight line pipe. So we obviously have to know how many feet of pipe we have. This is usually given to you in miles, and you have to convert it to feet. And then you also have to find the equivalent length of the fittings. And this is a table. You work this kind of like a budget. How many fittings you have, how many feet you add for each fitting. And then you multiply those two numbers together and you get a total for each type of fitting. And then you add all that together. So it's kind of like doing a little budget. And then you take that number of feet. So for every, like an elbow, sometimes it's adding 14 additional feet for every elbow. So if you did, you had 16 of those, you would do 16 times 14, and that's how many feet you add to your system to make it equivalent to straight line pipe. So that's the two components that go into the length of feet. Q is the rate of water flow. We'll be doing some other formulas with Q later, but it's measured in gallons per minute. And usually that's just given to you, how many gallons per minute are flowing through your system. C is the Hazen-Williams constant, and there's a table. You need to know the material that the pipes are made out of and if they're new or old. And so that's really the two questions you have to answer to find the right value. And then D is the diameter of the pipe in inches. And this is not like most formulas in this case. This is in feet. This is gallons per minute. We don't have a unit for this number. It's just a number. And D, diameter, is in inches. Don't convert this to feet or you will make your answers wrong. So this is the formula we're going to be dealing with, and there will be an example in the notes, and then I will expect you to successfully calculate something like this. All right, one more thing I want to talk about is supply pressure and residence pressure, your residential pressure. So the pressure in your supply system, the target value is between 65 and 75 psi. This is a safe operating range, an expected range. If you're below this, you have to add pumps and things to increase the pressure. And if you're above this, you need to regulate it so that it is at this in this target range. You can go up to 150 psi, but at that point, things are going to start leaking and things are going to start breaking. So you don't want to get into this is like a maximum spike it can take of pressure. You want to live between these two numbers, okay? And that's for the supply. When it gets to your house, the residence, it gets throttled down to between 40 and 60 psi. That's what we want to see there in your house. And it can take a spike of up to about 80 psi. Once you pass that, you're going to have leaks and damage. Even though it would operate between 60 and 80 psi, we wouldn't want to do this because you're going to, ultimately the problem is you stress your system out and you also waste a lot of water because you'll have a lot higher water flow when things are turned on. So normally you want to live between these two numbers. Most neighborhoods, they target on the lower end of this to distribute more equally. So that's a little bit about expected pressures. So that's a real quick review of the Hazen-Williams calculations. I really wanted to give you this map. So this is worth having in your notes. Make sure you've got this, that where each component, what each component means and where it comes from, so you can find this and kind of understand why we need to know the amount of head loss due to friction here. All right, that's all I have for today. Thank you for watching.